Hello everyone, my name is VENKATA Tharun Vellanki and I am a graduate student in electrical engineering at California State University, Sacramento. Today, I am excited to share some insights into an innovative memory technology called resistive random access memory or ReRAM that could revolutionize how we store and access data in electronic devices. These are the contents I'm going to talk in my presentation. Firstly, I'm going to introduce about the semiconductor memory, like why semiconductor memories are important in modern electronics, and followed by resistive random access memory and the structure of ReRAM, working of ReRAM, and how the switching mechanism takes place in ReRAM and advantages and recent developments, and finally conclusion. The role of semiconductor storage. Semiconductor storage is foundational in modern electronics, powering devices from smartphones to digital cameras. As we rely more on these devices, the demand for more efficient and robust memory solution grows. Currently, DRAM and flash RAM memory dominate the market, but they face significant challenges, particularly in technological scaling. For example, consider your smartphone which uses these memory types like DRAM or flash RAM. As phones get slimmer and more powerful, manufacturers struggle to keep up with the required memory capabilities without increasing the size or the cost. That's why we use the ReRAM. Introduction to ReRAM. ReRAM is a type of memory star technology. Memory star limits or regulates the flow of electrical current in a circuit and remembers the amount of charge that has previously flowed through it. ReRAM is also a type of non-volatile memory that utilizes the resistance of materials to store bits. Unlike traditional memories that relies on electron charge states, ReRAM operates by changing the resistance across a dielectric solid state substance. For example, imagine a light dimmer switch that adjusts the brightness of your room light based on how much you turn it. Similarly, ReRAM adjusts the resistance to store bits or data. Structure of ReRAM. ReRAM is typically structured in metal insulator metal MIM setup. Simply we call it as MIM setup. It consists of two conductive electrodes separated by insulating layer that can switch the state when voltage is applied, and the hardware includes either one transistor resistor or one diode resistor. Yeah, simply we will call it as 1T, 1R or 1D or 1R. This can be simply visualized as a sandwich, where the bed pieces are electrodes and the filling is an insulator layer that changes its properties based on what we fill in the sandwich. Working of ReRAM. Think of it as creating tiny roads within a city, where the flow of traffic represents the data storage, and the structure and the paths can be quickly changed, just like opening or closing roads to manage traffic flow. Similarly, ReRAM stores the data using ions and changes its electrical resistance rather than electrons. And the cells have two electrodes at which the ions dissolve and then precipitate. This changes the electrical resistance, which can be exploited for data storage. ReRAM generates the defects in a tin oxide layer known as oxygen vaccines, which can change or drift under electric field. The motion of oxygen ions and vacancies in an oxide is analogous to the motion of the electrons and the holes in a semiconductor. A dielectric can be made to conduct through a filament or conduction path formed after application of sufficiently high voltage. The conduction path can arise from vacancy or metal defect migration. Once the filament is formed, it may be reset or set. Low resistance path can be either homogeneous or localized. They can be distinguished by measuring the area dependency. Switching mechanism in ReRAM. ReRAM can switch between states using either unipolar or bipolar mechanisms, where the set or reset process occurs due to the voltage polarities applied across the electrodes. Unipolar. The switch direction does not depend on the polarity of the applied voltage. Bipolar. Sensitive to the polarity of the applied voltage. Reset and set occurs in opposite polarity. And finally, electron forming. Here, it not needed if the switching materials have inherent defective links or oxygen vacancy reservoirs. And for example, it's like an reversible door that can swing both ways depending on how you push or pull it, represents the set or reset states. Resistive switching property observed in transition metal oxide materials including binary oxides such as titanium oxides and vanadium oxides. And the below diagram illustrates current voltage characteristics for both unipolar and bipolar switching modes. And here the electron forming not needed if switching materials have inherent defective links or oxygen metal vacancies reservoirs. Advantages of ReRAM. Firstly, ReRAM has excellent scalability. With its simple structure, ReRAM can be more easily scaled down to smaller nanometer process compared to flash or DRAM. This is for continuing the trend for miniaturization in electronics. And secondly, it performs at very high speed. ReRAM can perform read and write operations at much higher speeds compared to flash RAM or DRAM. This speed enhancement is crucial for applications that require rapid data processing and low latency. And the next one is endurance. ReRAM typically offer greater endurance than flash RAM, with the ability to withstand a higher number of write cycles before the memory cell begin to degrade. This makes it more suitable for applications where data is frequently updated. And the next one is its energy efficiency. ReRAM consumes less power during both read and write operations, make it an ideal candidate for the use in mobile devices and other applications where the power conservation is critical. ReRAM capable of storing up to 1 TB of data on a single chip by 3D stacking. ReRAM operates at faster timescale and has a simpler, smallest cell structures, and it is a good option for design catches. Consumes very less energy, approximately 20 times less extending battery life in devices. Fast read write capability of device few nanoseconds. Imagine a storing of library records in a device is no longer than a coin. That's the potential of ReRAM technology. Recent developments. Panasonic 8-bit microcontroller unit, simply we call it as MCU. It is embedded with resistive random access memory. This technology is integrating ReRAM directly into an MCU can significantly enhance the speed and efficiency of data storage while reducing power consumption. This could be particularly beneficial in low power and high performance applications such as wearable electronics or IoT devices. And another multinational company, Samsung, has developed a ReRAM with 3D cross-point architecture. Samsung breakthrough likely involves stacking memory cells in a three-dimensional structure increasing density and storage capacity while possibly reduce the latency and energy usage. This could be a game changer for high performance computing and storage solutions. And also Intel and Micron's 3D X-Point technology. This technology is designed to fill the gap between DRAM and traditional storage, offering much faster read-write speeds than NAND flash memories. And higher durability and endurance. It is ideal for applications that require rapid access to large volumes of data, like real time data analytics or high speed transactions. ReRAM is indeed an important technology in the memory landscape. It lies in its ability to deliver non volatile, fast, and energy efficiency memory storage with high density.
it's a promising alternative to traditional flash memory because it can offer fast read and write speeds, lower power consumption, and greater durability. However, the primary barrier to widespread is the cost. Manufacturing ReRAM currently involves expensive materials and processes, which makes it challenging for it to compete with established technologies like NAND flash. However, there are also technical hurdles related to the consistency of switching behavior and device variability that need to be resolved to make the ReRAM commercially at, at large scale. Despite these challenges, research and development in this area continue as it holds potential benefit for next generation computing applications, particularly in embedded systems. And finally, thank you for giving this opportunity.